Very good morning, student. Okay, today we can continue our topic of CET, that is the topic of physics, that is friction in solid and liquids. Okay, so now yesterday we have learned about the friction in solids. Okay, and in that friction in solids, particularly we have learned about the types of friction. Which are the different types of friction that we have learned? That is the kinetic friction, that is the static friction, kinetic friction, then now rolling friction. Okay, so these different types of friction that we have learned, the coefficient of friction that we have calculated. Okay, today we can proceed for the, that means friction in liquids. Okay, but first of all, before proceeding to that friction in liquids, first point we have to learn about what is exactly pressure. Okay, so pressure is particularly, that is a scalar quantity, and it is defined as, it is denoted by P, and it is defined as P is equal to force exerted per unit area. Pressure is the ratio of force per unit area, so that is called as the pressure. So what is the SI unit of pressure then? SI unit of pressure is Newton per meter square, or CGS unit is dyne per centimeter square. And what is the relation between SI and CGS system of that units? 1 Newton per meter square is equal to 10 dyne per centimeter square. Okay, so that is the relation of that your pressure. Okay, so now what are the dimensions of pressure? The pressure will be force per unit area. Dimensions of force are M1 L1 T raised to minus 2 upon area L square. So that is equal to M1 L raised to minus 1 T raised to minus 2. These are the dimensions of your pressure. And pressure is which quantity? It is the scalar quantity. Okay, so this is all about that your pressure. Okay, once you got that pressure, then now question arises, sir, what is exactly fluid? Okay, because while you are learning the friction in liquids, so then there may be a liquid as well as fluid. Okay, so now sir, what is exactly fluid? Okay, definition of fluid is like this. The fluid is any substance which begins to flow when some external force is applied on it. Okay, means when some external force is exerted or exerted force is acts on it, then that substance which begins to flow, so that is called as the fluid. Okay, so now generally liquids and gases are the best examples of fluids. Okay, so these are the fluids. Okay, so now sir, what are the other characteristics of the fluid? Okay, the fluid do not have their own shape. Okay, fluid do not have their own shape, but they have the shape of container. They don't have their own shape, but they have the shape of the container. That is a very important property of that fluid. Okay, so they do not have specific shape, but in which container you are taking to that liquid or that fluid gases, so then that will be the shape of that container. Okay, then the next point is, that means their molecules, they are moving in a random motion. Their molecular motion is a random state of motion. Okay, in liquid or gases, all the molecules, okay, the molecules have a random state of motion. A random state of motion means in any direction they are going to move. They do not have a specific direction. Randomly they are moving here and there, like as in liquid Brownian motion. Okay, the same thing. The gases have also this type of motion. They are called as the random motion. Okay, so now the fluid in a container possesses the weight. Okay, fluid in a container container possesses weight. Okay, and so therefore as the fluid have the weight, they exerts the force on the base of the container. Okay, so that will be the another property of the your, that means your fluid. Okay, and not only they exerts the force on the, that means your base of the container, but they will also exert the force on the walls of the container. Okay, so that is the very important point about that fluid. Okay, and the force is always perpendicular to the normal area, okay, on which it acts. Okay, and whatever the that force, they will be that force will be always acts normally on which area they falls. Okay, so that will be the condition of that your fluid, or these are the characteristics of that your fluid. Okay, so the normal force may not be uniform. Okay, so the next point is that normal force, that next property is normal force is not uniform, over a given area. Okay, it is not uniform, normal force is not uniform over given area, it is not uniform over given area. So therefore we are taking average force. So therefore average, we can consider average pressure. Okay, average value of that pressure will be, okay, so then given area, so therefore average force value of pressure is taken to be, okay, average value of pressure, P average, will be taken to be force per unit area. Okay, so actually what happens, the normal force is not uniform all over the surface of a given area. So therefore we are taking the average value of pressure. So these are the some characteristics of that your fluid. Okay, once you got the idea about the your pressure and the what is the fluid exactly, then we are coming to the point, sir, how we can calculate the pressure exerted by the liquid column. Okay, pressure exerted by liquid column, pressure exerted by liquid column. Suppose I want to find out how much pressure is exerted by the liquid column. What do you mean by liquid column? Suppose if you are taking any container, and into that container if you are filling that liquid, so then liquid will be acts like as a liquid column. Suppose in any vessel, whatever the air is there, so there air will be acts like as a air column. The same thing, when you are filling the liquid into the container, it will act like as a liquid column. So then now what will be the pressure exerted by that liquid column on the base or on the walls of that container? How much that force will be exerted? So if I want to find out that force exerted by the liquid column on the container, what I have to do, I have to consider a one container first. Okay, that what will be the shape of the container will be like this. Okay, so this is the shape of the container. Okay, so here in that case I will fill the water into that container. Okay, so this is the way how you are filling the water into that container. Okay, and now when you are filling that water up to particular height is supposed to be h, then what will happen, so this liquid column, this will be acts like as a liquid column. Now it will exert some pressure, okay, on the walls of the container. Okay, so this will be the area. Okay, so this will be the area. So now if I want to find out, means here how I am calculating the pressure exerted by the liquid column. If suppose this is one of the container, okay, one cylindrical container if I have considered, and if I fill some water inside the container, okay, no doubt the water has been filled up to the height is supposed to be h. This is the base area, okay, or area of that base of that container. And so as this is the liquid column, so this will be exerts pressure on the base of the container. So how we can calculate the pressure exerted by the liquid column? So that will be the force acting per unit area. Okay, area of base F by A, or we can also say that pressure is equal to F by A. Okay, so that will be the pressure exerted. But now, if suppose I will consider rho is the density of the liquid. Rho is the density of a liquid, okay, which we have considered into that container. Then now force can be calculated by using the formula m into g, where m is the mass of the liquid, g is the acceleration due to gravity. But as density is equal to mass upon volume, so therefore mass is equal to density into volume. Okay, V is the volume. How we can find out the volume of that your liquid or that liquid column? So I know the volume of the liquid will be the volume of the container in which liquid has been filled. Up to what portion you have filled that liquid. So now if A is the area, H is the height, so then mass can be calculated by using the formula mass is equal to density into volume will be area into H. Okay, so mass is equal to rho into A into H. So therefore what will be the value of force? So therefore force is equal to mass will be rho AH and into G. Okay, so therefore if this is equation number 1, from equation 1 I can say pressure exerted by the liquid column on the walls will be force per unit area, that is rho AHG divided by area. Area will get cancelled. So the pressure is equal to H rho G. Okay. So what is the pressure exerted by the column? P is equal to H rho G. So that is your equation. So now here in that case we can say that pressure exerted depends upon height of the liquid column. Okay, dependent factors. Okay, first factors, pressure exerted, okay, exerted depends upon, कशावर depends करतो तो पहिल्यांदा height of the liquid column, height of liquid column. Second, it depends upon density of liquid. It depends upon height of the liquid column. It depends upon density of the liquid. Okay, it does not depends upon the size and shape of the container. It depends upon the rho, that is H, and G is the acceleration due to gravity. Okay, so that on the surface of Earth gravity will be the same, that is 9.8 meter per second square. So this is way how we can calculate the pressure exerted by the liquid columns. Okay, once you got that pressure exerted by the liquid column, then we are coming to the point. Next point is very important point, that is the hydrostatic paradox. Okay, what is that point? Hydrostatic paradox. Okay, in fluid mechanics, or we can say that friction in liquids, the hydrostatic paradox is very important paradox. Okay, you know hydro means liquid, water. Hydrostatic paradox. Okay, hydrostatic paradox. Okay, hydrostatic paradox. Sir, आता काय है हा paradox? What is that exactly? That paradox. Paradox means something is different, means which we cannot, that means thing we cannot assume, we cannot consider, and that things we are getting. So that is called as a paradox. Okay, means our thinking is different, but we are getting the result is different. So that is the paradox. And that too hydrostatics. Hydro means water. Statics means in the rest position. Means water is in the rest position. There is some paradox is going on. So that is called as the hydrostatic paradox. Sir, what is that paradox? So see here, the hydrostatic paradox is telling the force exerted per unit area or pressure exerted by the liquid column on the base of the container, on the same base of the container is the same, though that we have taken that liquid in a different shapes, but same height, means having a different volumes and different weight. Okay, means though the weight of the liquid or volume of the liquid in a different shape of container is different, but still the pressure exerted on its base will be remains the same. Now question arises, sir, how that can be possible? Because if the liquid is a different, so the naturally weight is the difference, and so therefore naturally the pressure exerted should be the different. But this thing is not going on. The pressure exerted by that liquid column on the base will be remain same, though the volume or weight of the liquid is different in a different shape of container, but having the same height. Okay. So now, sir, how this paradox is there? So that is the hydrostatic paradox. Okay, for that getting that paradox, you should first of all consider, sir, what exactly sir is telling. So suppose I am taking the three different shape of container having the same base. Okay, same base area. Okay, so now, so see here, this is the first container, second container, third container. Okay, this much, and this much. Okay, having the same base. Now see a first container I will draw like this, cylindrical container. Second container I will take like this. Okay, little bit slant, base is the same. Okay, and this container is again slant, base is the same. Okay, but height of that liquid filled in that three container is the same. Okay, so this is the three containers, and they are filled with the water. Okay, here. Okay, they are filled with water. So now height H here. So for this container also height of the liquid. This container also height of the liquid. Okay. So now in that three containers height is the same, base is the same, but shape of the container is different. Now can you think here, can you imagine which liquid or container on the base of that container pressure exerted will be more? Now what you are thinking here I know. According to you, sir, middle container which consists of more water, so therefore it will exert the more pressure on the base of that container. And if you want to measure, if I will connect your pressure meter for all these three containers. Okay, here 1, 2, 3. 1, 2, 3. Now your thinking will be, sir, this shape will be the little bit that means consist of large quantity of water, so therefore the pressure meter will show here it will be maximum. So suppose this is figure 1, figure 2 and figure 3. Okay, so these are your three figures, and so therefore according to you that here the pressure will be more, you are thinking here the pressure will be less, and here the pressure will be in between that. But here according to this paradox, what it is telling, if you are filling the liquid in a different shape of container having the same height, the force per unit area, okay, on the base area or pressure exerted by that liquid columns on their base will be remains the same, or that pressure will be shown by that pressure meter will be remains the same. Then now you are surprising here how these things happen, sir, here. How the pressure will be that means same, though the liquid contains into that three containers will be different. So that is the paradox. So I will explain to you. Now you see here, first of all you have learned the property of liquid, that means any fluid or liquid. When you are filling the fluid or liquid inside the container, then at that time what will happen? Liquid exerts the force on or pressure per unit area on that, or force per unit area or pressure on that walls of the container or base of the container is normally means in perpendicular direction. Okay, so that is the property. And meanwhile, according to Newton's third law of motion, the walls or the base will also exert the force on that your liquid or then to that fluid. Okay. So now in the first container, if this is the very straight container, that is the cylindrical container, if you are filled with certain height, that is H. then now no doubt this water will exert the pressure on the walls in this direction. Okay, so that will be the pressure exerted by the wall. Okay, here in that direction. Okay, so now if this is the pressure exerted by the walls into that direction, okay, so that is what exactly is going on. So that your pressure exerted by that liquid on the wall will also exert a reaction force on that liquid. Okay, and this will be in a normal direction. Okay, so this will be the in a perpendicular direction. So now whatever the liquid column will be there, so that much liquid column of that height h will be exerts the pressure, and that pressure will be denoted by the pressure meter. So I have measured that pressure. Now here if I can think, so here in that case, here again the liquid in the second container, the liquid will again exerts the pressure. Means now suppose if I will simply here in that case, if this is the horizontal vertical surface, a straight line, so there here exerted by the liquid, here in this direction reaction force is in this direction, so they are parallel to each other. Okay, in second case surface is like this, slant surface. Now what happens, liquid again exerts the pressure on that walls will be in a normal direction, in the normal direction. Okay, but now if I will consider the pressure exerted by the walls on that liquid is in a reaction force will be in the upward direction. Here the reaction and action force, they are parallel to each other, but here the reaction force, because you see here the container is now this shape, so therefore the resultant will be towards this direction. Means here I have to resolve these two components. Okay, so these are the two components we have to resolve. Okay, so sir, which are that two components? Okay, so which are that two components? So now what I have to consider, you see here in that case, so this is the first component, horizontal component, and this is the vertical component. Okay, horizontal and vertical. Now what happens, whatever the liquid which is exerting the force on that area, okay, on the walls, then at that time the liquid will also exert force on the wall will also exert force on the liquid. Okay, no doubt. In a horizontal direction, normal direction, it will be get balanced. But now there will be here extra amount of liquid is there. Then the vertical component of that liquid, okay, so that vertical component of the liquid reduces the downward thrust inside the liquid. Okay, so whatever the normal reaction, that means normal force is acting on that base, but now extra liquid whatever you feel here in that case. Okay, so here this is the extra part is there here in that case. Okay, these. So here in that both the sides, so this vertical component will reduces the what it will reduces downward thrust on that your base of the container. Means whatever the extra you feel, it will be balanced by vertical components of that your normal reaction, and so therefore the pressure will be this and this will be remains same. Now if I will take this shape of the container, in that shape of the container, what is going to happen? So here the walls of the liquid exerting force normally on the walls, and wall will exert the reaction force in the downward direction, because you see here this container is like this. Okay, like this. So therefore this will be in the downward direction. Again it has the two component. One is horizontal component, one is a vertical component. So what is going to happen here? So here in that case, okay, you feel, array, this much water is not there, so therefore it should be the less pressure. But now whatever the required, that means force, will be provided by the downward component, vertical component, which increases the what will increases the downward thrust. Okay, which increases the downward thrust of the liquid. म्हणजे मुलांनो जेवढा जो कमी आहे तो एवढा आहे, हा जो पार्ट आहे याचा म्हणजे नॉर्मल रिॲक्शनचा याने तो काय केला, भरून काढला. अँड सो रिझल्ट इज दॅट प्रेशर विल बी रिमेन्स द सेम. आर यू गेटिंग दिस पॉइंट? म्हणजे याच्यातला हा जो पार्ट होता हा इकडचा, तर ह्या दोघांचा ह्या व्हर्टिकल कॉम्पोनंटने त्या लिक्विडला काय केलं रे, अपवर्डला म्हणजे अपवर्ड डायरेक्शनला पकडून ठेवलं. म्हणजे त्याचा अपवर्ड कॉम्पोनंट म्हणजे व्हर्टिकल कॉम्पोनंटने तो जो तुमचा डाऊनवर्ड थ्रस्ट होता तो काय केला, रिड्यूस करून टाकला. म्हणजे तो जो एक्स्ट्राचा होता तो रिड्यूस केला आणि इकडे जो कमी पडत होता तो इन्क्रीज केला व्हर्टिकल कॉम्पोनंटने. सो दिस इज द वे हाऊ दॅट थिंग्स द बट इन ऑल दॅट मीन्स in all the three containers, though the shape is different, means volume of the liquid is different, weight of the liquid is different, but still the pressure exerted on that base will be same. So is it a paradox? Yes, means whatever we are thinking, but we are getting the different answer. That means pressure will be remains the same in all the three containers. So this is the hydrostatic paradox. Okay, once you got the hydrostatic paradox, then we are coming to the point, sir, what is the atmospheric? Are you getting my point? What is that? Hydrostatic paradox. Okay, म्हणजे मुलांना एक सोप्या भाषेत जरी तीन कंटेनर मध्ये लिक्विड वेगवेगळं होतं तरी प्रेशर मात्र सेम होता. सो दॅट इज द पॅराडॉक्स. ओके, नाउ once upon that means once you got that things, then now we are coming to the point, sir, what is atmospheric pressure and gauge pressure. आता हे दोन प्रेशर काढायचे, atmospheric and gauge pressure. Atmospheric pressure and gauge pressure. Okay, sir. Sir, then now what is atmospheric pressure? Actually, pressure exerted by the atmosphere is called as the atmospheric pressure. Okay, in simple language, because you know around our earth, so these are the gases are there. Okay, so that whatever the gases are there around the earth, they are creating or they are producing the atmosphere, and when this atmosphere exerts the pressure, that is called as the atmospheric pressure. Okay, so now once you got that atmospheric pressure, so how much that atmospheric pressure is there? That pressure is near about, you know, atmospheric pressure is 1.013 into 10 raised to 5 Newton per meter square or Pascal. Okay, so that will be the atmospheric pressure. Okay, so now I want to find out that atmospheric pressure by using the mercury barometer. First of all, we want to find out that is by using the mercury barometer. You know, barometer is the device which is used to measure the pressure of the liquid. Okay, so how we can measure the pressure? Pressure of atmosphere can be calculated. Pressure of the atmosphere can be calculated by using the device that is called as the barometer. Okay, means here one thing is very sure, that we can use the for calculating the, that means your atmospheric pressure, we have used to barometer. Okay, and now which barometer we are thinking about? Mercury barometer, and which has been invented by the Torricellis. Okay, so therefore it is also called as Torricellis barometer. Okay, Torricellis barometer. Okay, Torricellis barometer. Okay, for measuring atmosphere. He is an Italian physicist. Okay, and he has given that barometer, so therefore it is called as Torricellis barometer. Sir, how that Torricellis barometer is there? Okay, you want to learn and how to, so that he has used to measure the atmospheric pressure. Actually, Torricellis has considered a one tube having the length of 1 meter. Okay, this is one tube having the length of 1 meter, and this tube he has closed at one end. Okay, actually here he has taken this tube, he has taken the tube which was closed at one end, and inside that tube actually he has filled the clean and dry mercury. Okay, and now that means when he has filled the clean and dry mercury, then by using the thumb open end he has used the thumb, and then he has inverted that tube, 1 meter tube, inside the dish which consists of again mercury. Okay, म्हणजे मुलांनो बघा त्याचे आता कन्स्ट्रक्शन कसं होतं बघा. ओके, हे तुमचं डिश आहे आणि या डिश मध्ये मुलांनो आता त्याने काय केलं रे, इथं ही मर्क्युरी टाकून दिली. आता इथं मर्क्युरी ही पण एक डिश होती मुलांनो, याच्यात पण मर्क्युरी होती. ओके, आणि ही सुद्धा मर्क्युरी त्यांनी इथे अशी फील केली आणि कुठपर्यंत फील केली होती मुलांनो 1 मीटर पर्यंत अशी त्यांनी फील करून टाकली. ओके, पण काय झालं माहितीये का रे, once yes that means inverted that tube inside the your mercury. Okay, so here it was also mercury. Okay, here also mercury, this is also mercury. Okay, but that this is the glass tube having the length of 1 meter. Okay, now when he has inverted that tube inside the your container, then at that time, so up to the height h is equal to, that is near about 0.6 meter, or at a height of, means the mercury level falls at the height of 76 centimeter. Okay, म्हणजे मुलांनो ही मर्क्युरी सरळ अशी खाली आली आणि तिची हाईट किती राहिली रे, 76 सेंटीमीटर above the level of mercury into that dish. Okay, and here above that, here naturally what it has been created, a vacuum has been created, and that is also called as Torricelli's vacuum. What is that? Torricelli's vacuum. Okay, मग मुलांनो हा टॉरिसिलिस व्हॅक्यूम त्या ठिकाणी काय तयार झालेला, काय झालं मुलांनो, तयार झालेला आहे. ओके, आणि हाईट किती पर्यंत आली ती खाली 0.76 सेंटीमीटर पर्यंत आली. ओके, मग मुलांनो त्यांनी काय केलं माहिती का, ही जिथला एक पॉइंट त्यांनी कन्सिडर केला, त्याला ए म्हटला, इथे एक बी पॉइंट घेतला आणि सॉरी इथे एक बी पॉइंट टाकला आणि इथे एक सी पॉइंट घेतला. सो ए बी सी, these are the three different points he has considered here in that case. Now pressure here, as the vacuum has been created, so therefore pressure at point A will be 0. Okay, as there was the vacuum, so therefore pressure at that point A will be 0. Now at point C, pressure is the atmospheric pressure. Okay, at point C pressure, because it is open to the atmosphere, so therefore atmospheric pressure. But B point and C point have the same level. Therefore pressure at B is equal to pressure at C. Okay, so that pressure at B is equal to pressure at C, and that is equal to atmospheric pressure. Okay, so now pressure at B, but pressure at B can be calculated by using the formula, that is pressure at B can be calculated by using the formula pressure at A plus pressure at A plus pressure due to liquid column, that is pressure due to mercury column, so that is H rho G. Okay, H rho G. Okay, so that is the pressure. Therefore, okay, but pressure at A will be 0, so therefore pressure at B is equal to H rho G. But what is the pressure at B? That is the atmospheric pressure. So therefore I have to consider here, and pressure at B will be atmospheric pressure, and that is equal to H rho G. Okay, because pressure at C and pressure at B will be the same, so therefore it has to be considered as the atmospheric pressure. And now, so that atmospheric pressure can be calculated by using this formula H rho G. What is H here? H is the height of mercury level from the sea level, that is 76 centimeter or 0.76 meter. Density of liquid will be 13.6 into 10 raised to 3 kg per meter cube, and G is equal to 9.8 meter per second square. So therefore atmospheric pressure is equal to 0.76 into 13.6 into 10 raised to 3 into 9.8, and if you will calculate that your all this answer, so 1.013 into 10 raised to 5 Newton per meter square, or this is also given by Pascal, so therefore that will be pressure, atmospheric pressure will be given by the that means magnitude 10 raised to 5 Pascal. That is also, we can say that that is the atmospheric pressure. Okay, so this is way by using the mercury barometer we are able to find out the, that means your which pressure, that is the atmospheric pressure. Okay, once you got that atmospheric pressure, then now if you want to find out the pressure exerted by the gas, so that can be calculated by using the another device. This is the Torricelli's barometer, okay, mercury barometer, that which we have learned. Then now if I want to measure the pressure of the gas, so that can be calculated or that can be measured by using the open tube manometer. What is that name? Open tube manometer. Okay, so that is the device with the help of which we are able to find out the pressure exerted by the gas. Okay, so now how to find out that pressure exerted by the gas? By using the open tube manometer. Okay, so now for that what I will consider now is here. Suppose if I draw that manometer, so this is the vessel, gas containing vessel. Okay, and now to that gas containing vessel, if I will connect a U tube, okay, U-shaped tube. U-shaped tube will be in a such a way that it will be in a such a way that this tube will be like this. Okay, you see here. This is the nature of the tube. That U-shaped tube will be open at one end, okay, open to that atmosphere, and another end will be connected to the vessel. Okay, so here there will be a gas, and if I want to measure the pressure of that gas, okay, so that for that we have used the open tube manometer. Okay, so now in U tube we have filled a liquid. Okay, we have filled some liquid here in that case. Okay, so the pressure of the gas will be same as the pressure at point A. Suppose this is the pressure at or at this is another point B. Okay, so this is the another point C. Here that means open to the atmosphere, so therefore it will be exerted pressure due to atmosphere. This height of U shape will be H. Okay, so this is the open tube manometer now. Okay, again I will say it consists of, that means what is that open tube manometer? It will be used to measure the pressure of a gas enclosed in a vessel. Okay, it consists of U tube having the, that means in a such a way that it will be connected, or one end is open to the atmosphere, another end is connected to the that your vessel which consists of that gas. Okay, and in that tube you have filled some liquid. Okay, and now if you can see here in that manometer, one thing is very clear: pressure in that gas will be same as pressure at point A, and pressure at point will be same as pressure at point B, because they are at the same level. Okay, so therefore, but now sir, how much pressure at point A is equal to pressure at point B? Pressure at point B is equal to pressure, atmospheric pressure, means pressure at point C, plus H rho G. Okay, plus H rho G. We can also say that pressure at point A is equal to pressure at point B. Okay, first of all you can say like this also: pressure at point A is equal to pressure at point B. But pressure at point B is equal to pressure at point C plus H rho G. And pressure at point C will be the atmospheric pressure. Okay, so that will be the atmospheric pressure. And now, so that pressure PA plus H rho G is equal to total pressure, that is the atmospheric pressure plus H rho G, and that total pressure is also called as absolute pressure. Okay, this is the total or absolute pressure. Okay, so total or absolute pressure, okay, is nothing but the pressure at any point, total pressure, total or actual pressure at point P. Okay, it's called as the absolute pressure. Okay, means P is equal to PA plus H rho G. At any height, if you want to calculate the pressure exerted by the liquid column, then how we can calculate the pressure open at the open end? There will be the atmospheric pressure will be there, and due to the height liquid column, H rho g will be there. So PA plus H rho g will be the absolute pressure or total pressure. And then, sir, what is Gauss pressure? What is the Gauss pressure? Okay. If I want to find out the Gauss pressure, then how we can calculate? So you can just subtract from atmospheric pressure from the total pressure, means P minus PA. If I will take this side, then it will be H rho g, and P minus PA means total pressure minus atmospheric pressure. It will give you Gauss pressure, and that will be H rho g. But here H is the height of that liquid column, rho is the density of that liquid, and G is the acceleration due to gravity. Okay, so therefore Gauss pressure is the difference between the actual pressure at that point and from the which pressure, actual pressure, from that your atmospheric pressure. Okay, actual pressure minus atmospheric pressure will gives you a Gauss pressure, and most of the pressure measuring device, they are measuring the Gauss pressure. For example, in the tire, if suppose I want to measure the pressure, so that pressure that we are using the device that measure it as a Gauss pressure. Okay, and now this also for the blood pressure also, so we are using the Gauss pressure. Okay, spirometer, so that will be SpHyGOmeter. Spirometer is also device to use the measure of blood pressure. So that is way how you are using the Gauss pressure, means pressure due to height. Okay, once you got that things, then we want to find out that means your applications of Pascal's law. What is the Pascal's law? But before that, I will take one or two examples on that your manometer, as well as that means atmospheric pressure, Gauss pressure. Okay, so you please take the sum now. Okay, I will give the sum to you. So first sum will be, write down. First sum will be like this. Okay, so you please write down first sum. What is the pressure on a swimmer 10 meter below the surface of lake? What is the pressure of the swimmer? Means height is 10 meter below the lake. Now you see here, suppose this is the lake. Okay, this is the lake. This is open to sky. Okay, and now is open to atmosphere. And here this height is 10 meter. So at this point we want to find out pressure exerted. Now pressure at this certain height you will be, so this is the numerical. Okay, so how we can find out the pressure at that certain height? So that will be now actual pressure. P is equal to pressure at this point will be atmospheric pressure. So at particular on the surface of liquid, so that will be, or on that lake, on the above the lake, or we can say that which is facing to the atmosphere, that will be the atmospheric pressure plus H rho g. So that will be the Gauss pressure inside that. So Gauss pressure plus atmospheric pressure is equal to absolute pressure. The atmospheric pressure 1.013 into 10 raised to 5 plus height of the liquid column will be 10. Now rho, density of water, will be 1000. Okay, and G will be 10 we can take, or 9.8 we can take. Okay, 9.8. And solve that equation now. What the answer you are getting? Okay, so that will be 1.98 into 10 raised to 5 Pascal. Okay, or Newton per meter square. And so that is approximately 2 atmospheric pressure, because 10 raised to 5 means 1 atmospheric pressure, and 1.98 means approximately 2 atmospheric pressure. Okay, so that will be your right answer. Okay, म्हणजे मुलांनो at a particular height ला हा H rho g पण तुम्हाला घ्यावा लागतो. Okay, अजून एक सम देतो मुलांनो. This is the first sum. Now write down second sum. Okay, I will rub this sum. Then now take the second sum. Okay, so now the second sum is like this. Torricelli's barometer used Torricelli's barometer use mercury. Pascal duplicated it using the French wine density. Okay, French wine density. Okay, French wine density 984 kg per meter cube. Okay. Determine the height of the wine column for the normal atmospheric pressure. Okay, तर मग तुम्हाला त्याने ती हाईट त्यांनी तुम्हाला कोणाची विचारली मुलांनो, नॉर्मल दॅट वाईन कॉलम ऑफ द नॉर्मल ॲटमॉस्फेरिक प्रेशर. तर त्याची हाईट किती असेल. मग तुम्हाला एक गोष्ट माहिती आहे मुलांनो, काय रे, pressure exerted by the H height of the wine column will be same as pressure exerted by 76 centimeter of HG column. Okay, pressure exerted by H height of wine pressure exerted by H column of wine column will be same as pressure exerted by 76 centimeter height, 76 centimeter of height of HG column, ओके, म्हणजे दोघं सारखे असतात. आता याचा हा फ्रेंच कॉलम म्हणजे वाईन ना, याचा किती येणार रे, एच रो जी. मग ही एच काढायची, रो ऑफ वाईन इंटू जी इज इक्वल टू याचा एच. ओके, एच ऑफ हाईट ऑफ मर्क्युरी कॉलम ती 76 सेंटीमीटर म्हणजे 0.6 मीटर, रो डेन्सिटी ऑफ मर्क्युरी इंटू जी. आपण आता दोघे इक्वेट करू, हे दोघं वेगवेगळे आहेत मुलांना. हा एच आहे, हा तुमचा 984, जी सारखाच आहे मुलं 9.8. हा एच तुमचा किती असणार आहे, 0.76, आणि ही तुमची डेन्सिटी किती असणार आहे मुलांनो, दॅट विल बी किती येते रे, 13.6 into 10⁻3. So therefore H is equal to 0.76 into 13.6 into 10⁻3 upon 984. Okay, and that answer is near about 10.5 meter. What is that answer? 10.5 meter. Okay, so this is the your height of the, that means your wine column. Okay, म्हणजे तुम्ही दोघांची काय केली रे, comparison केली. Okay, so this is way how we have finished that point. Then now next point we can see the Pascal's law, but Pascal's law we can see later on. Okay, so we can stop here. Okay, and tomorrow we can continue for the Pascal's law. Okay, thank you student.